Okay, so I'm going to finish going over the review and then post this on D2L. So here are the questions we didn't have time to get to in class. So the first one was about domain and range, and so just quick review on that. Domain's going to tell you the values from left to right that are covered. We're talking about the x values, so you want to look at the x-axis. For the range, you're looking from the bottom to the top, and we're talking about the y values. So you want to focus on what y values are covered up. And then we'll talk about what makes a function in a second. So looking at the domain of this first one, so going from left to right, you can see that you have an x value of 3, and then 4, 5, 6, 7, and then those arrows indicate that it's going to continue going to the right. And so we include 3, so I'm going to bracket the 3, and then it goes to infinity, and we always use parentheses with our infinity symbols. Now, for the range, students sometimes make a mistake here. You see the arrows on the end, but they kind of think, oh, it's this from here to here, right? It's just from 1 to 3. But really, those arrows indicate that it's going to continue to go up and it's going to continue to go down. And so, really, it's going to go up indefinitely and it's going to go down indefinitely. And we always want to go from bottom to top. So, you need to put the negative infinity first to positive infinity, just like that. And so that is the range for that particular one. I'm going to continue doing domain and range, and like I said, we'll hit the function part at the end. So then on the next one, it's actually part B is kind of similar to part A, except that now the parabola is opening downwards. And so yes, it's going down, that's fine, but it's also going out to the left and to the right indefinitely. So the domain on this one's actually from negative to positive infinity. And then the range this time, we go down indefinitely, we go down, but we peak at 4. That's the highest we go in terms of our y values, right? Remember, range is y. So we have no bottom. It goes down indefinitely, but it only goes up to 4. And then we want to bracket that 4 in. And then on part C, we have a line, and on part of it, we have a closed circle, and on one, we have an open circle. The closed circle means that those points are included right there. And let's go ahead and figure out what that is as an ordered pair. Let's see, negative 1, 2, 3, 4, 5, 6, 7. So the x value is negative 7, and then it's down 1, 2, 3, down 3. So that's the ordered pair for that point. So remember, domain refers to the x values. So I'm starting here at negative 7, and it covers all the values out to here, which let's see, that is at 1, 2, 3, 4. This point right here is at 5, 1. And so domain, you just need to focus on those x values. So we go from negative 7 to 5, but the open circle indicates that you're approaching that point, but you never actually get all the way there. So our notation for this is going to be bracket negative 7 to 5, and then we have to put a parentheses on the 5. And that just means you're getting as close as possible, but you're never actually going to make it all the way there. And then for range, you just focus on the y values now. So the y values are from negative 3 up to 1. Once again, the negative 3 is part of my range because it's a closed circle, but the 1 is not, so I have to put that parentheses there. Okay, now determining whether they're a function or not. This is pretty simple. I mean, there's more to it than this, but the way you tell on a graph is you just kind of take a vertical line, and if it touches at more than one spot, then no, it's not a function. So this one would be no. This one would be, okay, that one's fine, that's a yes. And this one is a yes, and it doesn't touch it more than one point at a time. And so the first one is no, and then we have yes and yes. And so uh, what's taking place here is for a functional um, equation to be considered a function, you can only have one unique output for each input. So when x is, let's say, for example, let's see, 3, 4, 5. When x is 6, I have a problem here. I'm getting 1 and I'm getting 3 as an answer. And so that's a problem. So that doesn't qualify as a function. So functions are typically used to gather information. And if you're getting conflicting results, then that information might not be very useful, right? So, not that there's not an equation for this graph, because there is. It just doesn't qualify as a function. Okay, then down here we did basically just function notation, plug some things in. Um, let's see. Coming down here, we did knock out B. We'll go ahead and look at A and C. So A is actually kind of like B, but it's a little bit easier. So remember, the main thing is we do not want to divide by 0, and we do not want to square root negative numbers. And so let me elaborate on that, or well, I'll wait till we get to C. So looking at A, we don't want to divide by 0, so x cannot equal negative 10. Because if you plug in negative 10, what will happen is f of negative 10, I'm going to end up getting 7 over 0, which is undefined, right? And so we don't want to do that. And so basically your domain is everything but negative 10. So all the negative numbers you could think of, all the way approaching negative 10, but we don't include negative 10, and then union from negative 10 to positive infinity. So if you look at that, we just basically have everything from negative to positive infinity. We're just cutting out that negative 10. So, and if you looked at it on a number line, basically negative 10 would be right there with an open circle, but we have everything to the right, and we have everything to the left of that right there. Okay, so on part C, what's going on here is basically whenever you have a square root, you don't want to evaluate it at a negative value. So what you do is you just take the inside part and you say, you know what, that 3x minus 5, I can never allow that to be negative. So that expression always needs to be greater than or equal to 0, because you can square root 0, just not negative numbers. So we want it to always be greater than or equal to 0. So then from here we just solve this. So we'll add 5 to both sides. And then we're going to divide by 3 on both sides. And so now we say, you know what, the x values for that condition to hold need to be greater than or equal to 5 over 3. So whatever I plug in for x, as long as I'm larger than or equivalent to 5/3, I will not have any issues. Now, last thing though, we want to write it in interval notation. And so you could make a number line if you want, but this hopefully shouldn't be too difficult. So the domain, you just want everything bigger than or equal to. So the bracket, because we get to include the 5/3, and then to positive infinity. So those two things are basically the same thing. One's inequality notation, and then here's the interval notation. All right, so that takes care of page 1. See, page 2, I think we did all of page 2. That's good. Page 3. Okay, so we didn't finish everything here. We did part C, and we did the ones down below. So let's do these other 2 real quick. So let's see. All right, so looking at this graph, we're gonna, let's see, this one's actually not too bad. So the first transformation, you want to always do your left and right, which right here, this is going to cause us to go left 2, and then this is going to cause us to go down 3. So you take those points and just go left 2, down 3. So then we have another point right here, left 2, down 1, 2, 3, left 2, down 3. Let's see, left 2, down 3, and so on. And they should all it should form the same shape. So if you don't get the same shape, then you know something might have gone wrong, but everything looks good there. Okay, the next one might be a little bit more challenging just because we have a stretch taking place. All right, so I want to kind of keep this on my screen so I can see it as I do this. Okay, so once again, I have to do anything left and right first. So this time I'm actually going to move right 2. And then this times 2 technically causes a vertical stretch. And the best way to basically apply that is to multiply y by 2. And that will cause this graph to kind of stretch vertically. So taking that first point, we go to the right 2, multiply y by 2. Well, y is currently 0, so it's going to stay 0. Then this one, we're going to go to the right 2, and then multiply y by 2. So y is currently negative 2, but when I multiply it by 2, it's going to stretch down to negative 4. And then the 0, 0, we go to the right 2. Y is still 0, so multiplying 0 by 2 doesn't change anything, so that point's going to be right there. Then the 2, 2 point will move to the right 2. And then I multiply my y value by 2, so 2 times 2 is 4, so it's going to stretch it. And then the last point, we start at 4, 0. We move to the right 2. The y value is 0, so 0 times 2, well, that's still going to just be 0 for my y value, so nothing changed on that transformation part. And then we will connect our dots. And it's the same shape, but obviously it's stretched out a little bit, and it's because of the 2 that's in front right there. Alrighty, so then we'll move on to the last page. And so this here, we'll see if I have enough room to do all this. So the first one is not bad. You're just taking f of x plus g of x, and you just basically combine the like terms. So you're going to have x squared plus 3x plus 4x minus 5. And so when you combine those together, we're going to end up with x squared plus 7x minus 5. And that would be the first one. Now the next one, you have to be a little careful with that subtraction, and I'm going to try to fit it up over here. So this notation would be f of x minus g of x. And when you subtract the g of x, you want to subtract whatever that is, the whole thing. So you're going to want to put that in parentheses. So let's see. So for f of x, let's see, we get x squared plus 3x. And then we are going to subtract, and then you need to put the 4x minus 5 in parentheses, because we are going to need to distribute that to both parts of that. So then let's see, the first part stays the same. Then this becomes a minus 4x, and then that minus 5 actually goes to a plus 5. Then we're going to combine the plus 3x and the minus 4x. So we end up with x squared minus 1x, or just x, and then plus 5. So it's not necessary to put the 1 in front. You can, it doesn't make it incorrect, but it's not necessary. Okay, so then the next part, we're multiplying them together. So this is going to be f of x times g of x. And in this particular case, I think we're basically going to be foiling it. All right. So the way this is going to work is you take the first term and you multiply it by both of the other terms. So let's see, that'll give us 4x to the power of 3. And then x squared times minus 5 would be a minus 5x squared. So that's the first part. Then the second part, you multiply 3x by 4x, which would be a plus 12x squared. And then you multiply it by the minus 5 also. And so then that would be a minus 15x. And then last but not least, you want to combine those like terms in the middle. And so I'm going to go ahead and put our answer up above. So you have the 4x cubed. Then we have the plus 7x squared when you combine the two in the middle. And then you have the minus 15x. And there you go. Okay, let's see. Knock those out. So we just have these last three right here. Okay, so on number 11, the first thing we want to do is change this to y. So y equals 4x minus 3. Just makes things a little bit easier. Then we do the little switcheroo. So now we have x equals 4y minus 3. And then now we need to solve for y. So we'll start by adding 3 to both sides. I'm going to come up here where I have more room. So we're going to have x plus 3 equals 4y. And then we're going to divide by 4. And so we're left with y equals x plus 3 over 4. Or for our function notation, the f inverse is equal to x plus 3 over 4. Okay, our next one, we're going to have to be a little careful on this one because they're going to want us to give the domain of the inverse function. Um, so we're going to start off by the same thing. We're going to do y equals the square root of x minus 4 minus 2. And then we do a little switcheroo. So x equals the square root of y minus 4 minus 2. And now it's time to try to solve for y. So we'll start by adding 2 to both sides. We'll add 2 to both sides. And I'm going to come up over here. And so we're going to have x plus 2 equals the square root of y minus 4. And then to nullify the square root, we are going to square both sides. So we'll square both sides. And so we're going to just leave this as x plus 2 squared. You don't have to square that out. And then on the right, we're left with y minus 4. And then the last thing we're going to do is add 4 to both sides. And so we're left with x plus 2 squared plus 4 is equal to y, basically our inverse function notation. We're going to be left with x plus 2 squared plus 4. Okay, so then they do ask for the domain. And so the domain is just going to be the range of the original function. It's going to be the range of the original function. So if you look at the original function right here, we can do a little sketch of it. And so it's going to be what? That's going to be to the right 4 and down 2. And it's going to kind of look like this, right? It's going to look like that. And so if you look at the range on this, it's going from -2 up to infinity. And so that's what my domain would be for this right here. Oops, let's bracket that in. It's going to be from -2 to infinity. That is going to be my my domain on that. So it's just the range of this. So here's this. And the range of this was from -2 to infinity. And so the range of the original function is the domain of the inverse function, because that's the whole thing about inverse functions. You don't really want to overthink it too much, but really the x's and y's are just swapping roles. That's all it is. So my range is now my domain, and my domain is now my range. And so this is necessary because this inverse function is not a one-to-one function without this restriction on the domain. Okay, and then the last one, this one should not be too difficult. In order to find the inverse of a function, if you have x and y, it's pretty simple to find the inverse. Just swap it. Put the y where the x is and the x where the y is. And that just kind of reiterates what I was talking about up here with the domain and range switching. So it's the same thing here. If you want to graph the new function, you're just going to take these ordered pairs. So let's see, this was at -4, -5. Now we're going to put it at -5, -4 down here. And then let's see, this point right here was at -3, -3. Well, guess what? When you swap them, it stays at -3, -3. So that point's going to stay there. Then let's see, then we have this point right here, which is at 1, -2. We're going to flip-flop it. Now it's going to be at -2, +1. So it's going to actually be up here. Okay. And then the last one right here, this was originally at 4, -1. Now we're going to go -1 up 4. And it's going to be right there. And we'll go ahead and connect these dots. And there we go. And something that I've shown in class a couple times is what happens here is this is actually a reflection across the line right here, which is y, oops, which is y equals x. That's what that green line is right there. And that's basically the notation for the reflection, is that if you swap the x and y's, that's what happens. You get a reflection across that line right there. All right, I hope that helps. And if you have questions before Tuesday, just let me know, and I'll try to address them the best I can.